Last period we have seen how we take the derivatives of this implicit function. Now today we will see this another special function, that is the parametric function, and how we take the derivatives of that parametric function. So parametric function functional form is x is equal to f of t and y is equal to suppose phi of t is the parameter. So if here the theorem we are using to find the derivatives of the parametric function. So if x is equal to f of t, y is equal to phi of t, where t equal to parameter, so this type of the function is called the parametric function. That is, the function is defined by the general point of the curve, that is pxy, in terms of the parameter t. Now for this type of the function, parametric function, we use the theorem to find the derivative, that is dy by dx. You want to find the derivatives of y with respect to x. So dy by dx is equal to dy by dt divided by dx by dt. So you differentiate y with respect to t and divided by x with respect to t, will find the derivatives of this parametric function. Now if you want to prove this theorem, so very easily we prove this theorem by Leibniz definition. So let delta x and delta y be very small increments in x and y respectively with respect to increment delta t in t. Here t is the independent variable, x and y two independent of the dependent variables. Let x is equal to f of t and y is equal to phi of t. Since delta y upon delta x is equal to, you can write delta y upon delta t divided by delta x upon delta t. You can write like this. We have divided numerator denominator by delta t. Now you take the limits. So taking limits as the delta t tends to 0, so limit delta t tends to 0, delta y upon delta x is equal to limit delta y upon delta t divided by delta x upon delta t. So that is equal to, you can write limit delta t tends to 0, delta t tends to 0, delta y upon delta t divided by limit delta t tends to 0, delta x upon delta t. That is the theorem on the derivatives division of the function. Now here this limit delta t tends to 0, delta y upon delta x. As delta t tends to 0, delta x also tends to 0, and by definition of derivative, limit delta t tends to 0, delta y upon delta x is dy by dx. Limit delta delta x, delta t tends to 0, delta y upon delta t is dy by dt, and limit delta t tends to 0, delta x upon delta t dx upon dt. So putting in equation first from second and third equation values, we get dy by dx equal to dy by dt divided by dx by dt. That is the proof of this theorem, hence proof. So like this, we prove this theorem by using Leibniz definition, that is the second definition of derivatives. So we'll solve some examples for the application of this theorem of the parametric function. So solution, first example. So we have x is equal to here a cos cube t, y is equal to a sin cube t. So here x is equal to a cos cube t, y is equal to a sin cube t. That is the parametric function. T is the parameter, a is the constant. So variable and constant. So we have studied in the that is in the video introduction to the functions. Now differentiate with respect to t. So our requirement, you want to find dy by dx. So dy by dx is equal to dy by dt divided by dx by dt. So that is equal to, now you differentiate y with respect to t. So derivative of a sin cube t, a constant, sin cube means sin bracket cube. So that is power function. So 3 sin square t, and derivative of sin is cos t divided by derivative of x with respect to t. So a into 3 cos square t, and derivative of cos is minus sin t. So that is equal to, now this a 3 gets cancelled, cos square gets cancelled, sin for this square gets cancelled. So minus sin t divided by cos t. So that is equal to minus tan t. So dy by dx is equal to minus tan t. Now second example. So we have x equal to e raised to log sin 2 theta. So here theta is the parameter. Y is equal to e raised to log cos 2 theta. So we'll differentiate this function with respect to theta. So again here, instead of differentiating this immediately, so if we can simplify the function. Now e raised to log base is here e. So log and anti-log. So x is equal to, get simplified function sin 2 theta. Sin 2 theta. Y is equal to cos 2 theta. So it is the simplicity for the derivative. Now differentiate with respect to theta. So for parametric function, dy by dx equal to dy by d theta divided by dx upon d theta. Now derivatives of y, cos 2 theta. So cos 2 theta minus sin 2 theta, and into derivatives of 2 theta, 2 constant, theta is 1, divided by cos 2 theta into derivatives of 2 theta, 2 into 1. Now this gets cancelled. Sin upon cos is tan. So we are getting dy by dx is equal to minus tan 2 theta. So this is the derivative of this given function in second example. Now we will see the third example. If so, we have x is equal to a into bracket cos t plus t sin t. Y is equal to a sin t minus t cos t. So here t is the parameter, this is the parametric function. So we'll differentiate with respect to t. Now derivative of x with respect to t, dx upon dt, a constant into bracket. Now derivative of this cos is minus sin t plus. Now t sin t, you will product formula. So t constant, derivative of sin is cos t plus sin t constant, derivative of t is 1. So that is coming as a. Now plus and minus sign gets cancelled. So at sin at cos t. At cos t. Similarly, we will find the derivative of this y. So dy by dt is equal to a constant, derivative of sin is cos t minus t. Now derivative of cos is minus sin t minus cos t, derivative of t is 1. So plus and minus cos gets cancelled. Now minus minus this plus, so we get 80 sin t. So for parametric function, dy by dx is equal to dy by dt upon dx by dt. So that is equal to 80 sin t divided by 80 cos t. Sin upon cos is tan t. Okay, sorry. You want to find the derivative. So we are coming dy by dx is equal to tan t. Therefore, at t is equal to pi by 4, dy by dx is equal to tan pi by 4, so that is 1. So you want to find value at t is equal to pi by 4, so we put that value in that derivatives. Now fourth example, we have x is equal to e raised to cos 2t and y is equal to e raised to sin 2t. Now this is the parametric function with parameter t. So differentiate first with respect to t. So dx upon dt e raised to cos 2t and derivative of cos is minus sin 2t into 2 into 1. dy by dt e raised to sin 2t into derivative of 2t, derivative of this sin is cos 2t and derivative of 2t is 2 into 1. So that is minus 2 sin 2t e raised to cos 2t. This is 2 cos 2t e raised to sin 2t. For parametric function, dy by dx is equal to dy by dt divided by dx by dt. So 2 cos 2t e raised to sin 2t divided by minus 2 sin 2t e raised to cos 2t. So that is equal to 2 gets cancelled. So minus. Now here our required result is in this form, so x and y. So you want to eliminate the t. So since x is equal to e raised to cos 2t, so therefore log x is equal to e raised to cos 2t. Y is equal to e raised to sin 2t, therefore log y is equal to sin 2t. So we will introduce this value. So minus cos 2t is log x e raised to sin 2 is y divided by sin 2t is equal to log y from this result, and sin 2t e raised to cos 2t is x, so that is equal to minus x log x, y log x divided by x log y. So minus y log x divided by x log y, that is the result, hence proved. So we have u is equal to, u is the function of x, u is equal to, we have given sin inverse 2x divided by 1 plus x square, v equal to cos inverse 1 minus x square divided by 1 plus x square. Now here this is the inverse function here, and again the parametric function here, x is the parameter. So in inverse function, it will differentiate directly there, which is complicated. We want to take the derivatives of sin inverse, then you want to use u by v rule, etc. Here also same thing. So instead of that, we will go to the substitution. Now here expression 1 plus x square. So actually when expression is 1 plus x square, we are putting x is equal to tan theta. We are putting x is equal to a tan theta. So here we put this x is equal to tan theta, a is equal to 1. Actually this expression is the more weightage than this expression, other expressions. So theta is equal to tan inverse x. So u is equal to sin inverse of 2 tan theta divided by 1 plus tan square theta. P equal to, we get cos inverse 1 minus tan square theta divided by 1 plus tan square theta. So that is equal to sin inverse. You know this. Now here as sin inverse, here sin is required. Now you know this sin to theta formula in terms of tan. So sin to theta is 2 tan theta upon 1 plus tan square theta. So we can write here sin to theta. Similarly here cos inverse of, this is the formula of cos to theta in terms of that, cos to theta is equal to 1 minus tan square upon 1 plus tan square. So we can write cos to theta. That is our requirement. That is our requirement. So sin inverse and gets cancelled, we get 2 theta. And here we get again 2 theta. Now theta is equal to tan inverse. So u is equal to 2 tan inverse x and v is equal to 2 tan inverse x. Now very simple for the differentiation. So in inverse function, in that logarithmic differentiation, you solve the examples with imagination, with thinking in the mind. You take the proper decision. So differentiate now here. With where you are starting the derivatives, always you write differentiate with respect to x. So du upon dx is equal to 2 constant and derivative. So derivatives of u, now u is equal to 2 tan inverse x, v is equal to, we are getting 2 tan inverse x. That is, u is the function of x, v is the function of x. We are differentiating with respect to x. So we get du upon dx is equal to 2 constant and derivatives of tan inverse is 1 upon 1 plus x square. That is equal to 2 divided by 1 plus x square. Similarly, dv upon dx is equal to 2 constant into 1 upon 1 plus x square. So that is equal to 2 divided by 1 plus x square. So for parametric function, you want to find du upon dv is equal to du by dx divided by dv by dx. So that is equal to 2 divided by 1 plus x square and divided by 2 divided by 1 plus x square. So 2 gets cancelled, this 1 plus x square. So that is equal to remaining is 1. That is the result, hence proved. So like this, we'll solve this 5th example. Now 6th example, differentiate tan inverse x root of 1 minus x square with respect to sec inverse 1 upon 2x square minus 1. So that is, you want to find the derivatives of one function with other function. So you keep in the mind, when you want to find the derivatives of one function with respect to other function, use the theorem of this parametric function. So this parametric function theorem we are using to find derivatives of one function with respect to other function. So derivative of one function with respect to other function, use theorem of parametric function. So now we'll solve the sixth example. So in sixth example we have we'll take this let u equal to, first function suppose tan inverse x divided by root of 1 minus x square, v equal to sec inverse 1 upon 2x square minus 1. Now sec inverse 1 upon x, you know this cos inverse x, we have studied this rule in the introduction of the derivatives of this function of inverse, that is inverse trigonometric function. So we can write here cos inverse 2x square minus 1. Now here expression 1 minus x square. So you want to put here maybe sine or cos. Now you want to if we put sine, no problem, you will get it. If we put cos, then also we can get the result. But some if we you always choose proper, so selection must be there. So whether sine is used or cos is used, you want to think something there, and then you reduce the step of writer. So for that here now this tan inverse, so here sine is required, because tan is required and tan is equal to sine upon cos. So we put here x is equal to sine. We put here x is equal to sine. So we put x is equal to sine theta. So therefore theta is equal to sine inverse x. So u is equal to, we get tan inverse sine theta divided by under root 1 minus sine square theta. So that is equal to tan inverse of sine theta divided by root of cos square theta, identity, sine square plus cos square is 1. So tan inverse of sine theta upon cos theta. So tan inverse of sine upon cos is tan theta. So tan inverse tan gets cancelled. So theta. U is equal to theta. So u is equal to sine inverse x. A very simplified function, direct standard formula we are getting. On the same manner, we'll simplify here also this. So v is equal to, we get cos inverse of 2 sine square theta minus 1. Now when 2 sine square theta or 2 cos square theta term is coming, you recall the formula 1 minus cos 2 theta. So 1 minus cos 2 theta is equal to, you know this, 2 sine square theta, and 1 plus cos 2 theta, 1 plus cos 2 theta, that is 2 cos square theta. So this 2 sine square theta minus 1 is equal to minus cos 2 theta. This one we have taken here. Right. So 2 sine square theta minus 1. So cos inverse of minus cos 2 theta. Now cos inverse of minus pi minus cos inverse cos 2 theta. Second quadrant cos is negative. So that is equal to pi minus cos inverse cos gets cancelled 2 theta. So pi minus 2 sine inverse x. Now differentiate with respect to x. So du upon dx is equal to 1 upon under root 1 minus x square. dv upon dx is equal to pi 0 minus 2 1 upon under root 1 minus x square. So minus 2 divided by root of 1 minus x square. For parametric function, du upon dv, du by dx divided by dv by dx. Now we put these values. So du upon dv is equal to 1 upon under root 1 minus x square divided by minus 2 divided by under root 1 minus x square. This gets cancelled, so minus 1 half. Now here for this type of example, that is when you will find the derivatives of one function with other function, you always write the result in this form. So therefore derivative of tan inverse x upon under root 1 minus x square with respect to sec inverse 1 upon 1 2x square plus 2x square minus 1 is 1 minus 1 half minus 1. So like this you want to interpret the result when we will find the derivatives of one function with other function. Now seventh example, that is also the derivative of one function with other function. So seventh example we start. Let u equal to log 1 plus x square, v equal to root 1 plus x square. Differentiate with respect to x. So du upon dx is equal to derivative of log 1 upon 1 plus x square into derivative of 1 plus x square. 1 is 0, x square is 2x. So 2 divided by 2x divided by 1 plus x square. dv upon dx equal to root derivative is 1 upon 2 root 1 plus x square into derivative of 1 is 0 and x square is 2x. So 2 gets cancelled. So x upon under root 1 plus x square. For parametric function, du upon dv is equal to du by dx divided by dv by dx. So that is equal to du upon dx 2x divided by 1 plus x square, x divided by under root 1 plus x square. So that is equal to x divided by the root of this 1 plus x square upon root 1 plus this root is coming here. So 1 plus x square. So therefore derivative of log 1 plus x square with respect to root 1 plus x square is x divided by root 1 plus x square. So like this we want to interpret the result when we find the derivatives of one function with other function. So this is about the how we find the derivatives of these parametric functions. Very much thanks. You observe the video thoroughly, completely. Then you subscribe to this video so that you will get the continuous next videos. and practice some examples. So, minimum 2 hours practice is required for each type of the function in the derivatives. Then there is no problem. You will be the very strong in the mathematics. Thank you.